I hope my screen is visible, right, to all of you?
Yes, sir.
Yes, sir.
Okay. Yeah. So before to start the session, uh, anyone have any doubt? Yeah, Ananya have asked related to week 5. I just sit. Better to once you see your fault, that would be good, no?
Sir,
Yes, sir.
week 6 GA question number 6.
Week 6 GA. Okay, what is that question? Could you read out that? Is this the question?
Sir, question number 6, sir. X belongs to an R4 and it is a transmitted signal, and let Y belongs to R6 be the received signal,
Okay.
and the model is Y equals to Hx plus Z, and the matrix H given, and the question is to find R such that X equal to Ry, and the X cap equal to Ry, and there is a, and we have to calculate the left pseudo inverse HPI such that H transpose H inverse into H transpose. Actually,
Is
sir,
this question of maths too?
has sir, yes, sir, I solved this, but manually means uh, in the order the matrix given, I just multiplied and made inverse, and then it is just just laborious process, and actually, sir, I want to know, is there any smart trick? Yeah, or I am missing some concepts.
Is it maths 2 question? Pseudo inverse is in maths 2? Okay.
Yes, sir, maths too.
Okay, this is a old. Okay. So what is? Could you read out? I don't have this question. I have this on an older access. What is that? Could you read out again?
Sir,
Or
week
you can
6.
present your screen. Are you able to present your screen or the question?
Yes, sir.
The due date is over, right? Of week 6 for week 6.
Yes, sir, week 6 is over.
Okay.
Sir, is it visible?
Yes. Okay. 1 minute. Okay. It's visible, but not clear to me. 6 latex. Yeah.
I can present this question in mine.
Yeah, yeah. Please present because it's mobile view, no, so I'm not able to see properly. No, you so in this process you have to only follow this because it's already mentioned. No, H the pseudo inverse is H transpose H inverse to H transpose. Any other method? No. Yeah, I have to check it for the for other method. Okay.
So, sir, should I stop here?
Yeah, yeah. Okay, so I don't. No one have done. Only one person have joined the last session for week 7. We were discussing about the. Let me present my screen. Eigenvalues, eigenvectors, and the existence of eigenvalues, eigenvector. We have discussed till algebraic and geometric multiplicities. So anyone have gone through with the older session at least?
Yes, sir. We have gone through the lecture videos.
Oh, so that is so. Then it is fine. So all video lectures
No,
Sir,
sir.
I haven't.
or sorry, one can speak
I
up.
haven't.
Okay,
Last two left, sir.
okay. So the last one is actually computing the compute the by computer that is different. That is a Python. Can use it. The eigenvalues, eigenvector algebra. This one as the special cases. These two lectures are very important in the case of a kind of trick is you will find here that how if you have a bigger matrix follow a pattern, a particular pattern, then we can easily find the eigenvalues, eigenvector without computing a minus or going through with the a minus lambda I all. You don't need to go with all. You just see that if the particular matrix have this pattern like if the row is sum is row sum for all, sorry, each row sum is a particular number, fixed number is coming, then you can say that particular number is going to be eigenvalue eigen. So and the eigenvector corresponding is 1 1 1. You can tell it that it's depend on the the dimension of the matrix. So before to reach, means I was just giving the introduction that what is in these two lectures have like very special cases are there, and this will generally help a lot to find the eigenvalues, eigenvector for in the different scenario. Like you want to find the eigenvalue of a power k or a power 5. If you if you know the a matrix A and you know the eigenvalues of A, then you can easily find the eigenvalue of a power 5. Okay. Okay, so before to start, like anyone can tell what is eigenvalue? What is eigenvalue, eigenvector?
For sir, for any matrix, there exists some complex number lambda such that a minus lambda I is singular.
Okay.
And
Sorry.
for corresponding any lambda, uh, the null space of a minus lambda I, and we have to solve the null space, and the basis of the null space is the eigenvector corresponding to the lambda.
Okay, yeah. And okay, so the basis is basis of the null space is going to be this week 7 is for you are telling for any order of the matrix, or it is only for particular 2 cross 2?
It is, sir, we have solved up to 3 cross 3, and
Mm-hmm.
beyond 3 cross 3, it is very difficult for us.
Okay, yeah, that is the general idea even. And anyone can tell what is a geometric multiplicity and algebraic multiplicity?
The times the lambda occurs in the roots, that is the algebraic multiplicity of the eigen value, and the dimension of the null space of a minus lambda I is the geometric multiplicity of the corresponding lambda.
Yes, yeah, that is the proper definition. Yeah. Anyone else want to tell this? This is the only definition of eigenvalue and eigenvector. And whatever we have discussed in the last session, I have discussed. This is the only thing. Like even the session is sorry, the contents are only discussing, telling about the eigenvalues, eigenvectors, and their algebraic and geometric multiplicity. And this is the case only if you have a matrix, then let's say even a matrix or a linear transformation if we have from let's say Rn to Rn. So now I am saying any Rn, because in the previous time, in the previous week, you have seen for R2 to R2, but now it's in extension form. And if you have a linear transformation, then we can easily find the matrix representation of it. I hope you know how to find it. and the order of the matrix is going to be n cross n. So if you have matrix representation of T which is A, then there would, let's say there is a vector of this one, because both domain and codomain spaces are the same. So let's say I have a vector V in here, and what is happening, even if I'm finding the image of TV which is just scaled up with the vector, it is just scaling up the vector lambda time, which is a scalar. So I'm finding the image, this is just scaled up. So this kind of thing is happening. So such vectors are called eigenvectors, and this particular number is called eigenvalue. So this is the same case is, even if you multiply with the vector with the matrix representation of T which is A, this we have like a very similar lambda time this V. And then again, you can send this to this side, and by this way you will get a method to find the eigenvalues eigenvector, which you know already, in 2 cross 2 at least. So if you send this one to this side, okay, this is equal to 0. So here in place of just lambda, sorry, this V, if I am writing this V, which is nothing but identity time V is, if I suppose I am multiplying this V with the identity matrix, I will get same V, right? Is it true?
Yes, sir.
So that means here is, you can say the hidden I is there. So you can now, you can take common V, then it will be outer, and you can say this is A minus lambda I, you will get. And you have keeping this side. So this matrix is important. Now what is the way, if you want to find this lambda, just find the determinant of it. Determinant of this matrix equated to 0, you will get the lambda, some polynomial in lambda, which is called characteristic polynomial. And let's say this p lambda is the polynomial is p lambda, which is called characteristic polynomial, and you can find the root. So it's depend on order. What is the order of this matrix? If it is n cross n, then this polynomial have degree n. Means this is an n degree polynomial, and you have to solve to find the lambda value, and that lambda value is going to be eigenvalues. So whatever here is the same for the, either you are thinking with this way in the linear transformation or in the matrix form, this is going to be same method to follow to find the eigenvalues. So I am doing this fast because last time I have discussed this one. I want to discuss this special cases. I have discussed till 4 lectures, I think, or 5. So here is whatever the value is going to be. This is that is going to be eigenvalue. So algebraic multiplicity is related to this one. That if you have a, while finding, you are getting a kind of this structure. Let's say let's say alpha is coming even in place of particular. Let's say alpha square is coming somewhere in the polynomial, in the while doing this, you are getting kind of this one, means, or different way, you are finding twicely lambda, sorry, alpha is twicely some other lambda 1 is this one, lambda 2 is some other, I mean it's coming twicely thricely, means how many times it's coming, your roots are, you can say that is, here is the algebraic multiplicity is 2. Just now he said no, that what is going to be algebraic multiplicity, and once you go, you will get here the eigenvalues, the null space of this one, okay, we will find the null space of it, of this matrix, and the dimension of the null space is going to be the geometric multiplicity for this eigenvalue, which for this eigenvalue alpha, lambda 1 or even. That is your algebraic multiplicity. It's just now also given the definition for algebraic and geometric multiplicity. So why I am this quickly doing this? The one we have seen in 2 cross 2, there is no change even. We have done already the weeks for week 2 cross 2. Here is slightly extension, but there is no change in the definition or any kind of. It is just we have done the more example on 2 cross 2. It is slightly extension for in place of n cross n we can do 3 cross 3, 4 cross 4, or any order of square matrix. Any square matrix means any order is going to be for the square matrix. Okay. So everything is saying whatever you have seen algebraic, geometric, eigenvalues, eigenvector. Let's move ahead to the special case of matrices. So before to start, anyone wants to comment something or say something? Not still not clear.
It's clear, sir.
Okay. So here is this lecture 5. We have discussed that what is the by hand calculating means you just do the a minus lambda I, find the determinant and equal to 0, find the roots. I just telling you the method, professor. So there is the relation also with the rank and eigenvalue. So this trick is most of the times you can use these tricks. Like suppose a matrix is bigger, okay? So you can see in the second this in this lecture, professor is telling the rank with the rank and matrix case. Suppose you have a bigger matrix, okay, of let's say 5 cross 5. You have a 5 cross 5 matrix, and it said that find the eigenvalues of it. So you will start doing with the a minus lambda I. Before to start do this, before a minus lambda I and determinant of it, doing this, can we think and can we say what is going to be rank for this? There is the relation with the rank and the eigenvalues. What is the exact relation? Can anyone tell?
Sir, if it is full rank matrix, then 0 cannot be the eigenvalue.
Yeah. And if it is lesser than
And if it is lesser than n, then obviously 0 is an eigenvalue.
0 is going to be one eigenvalue. What is the rank here? Can you tell me what is the rank here?
So you didn't wrote the whole thing, na?
Sorry?
You didn't wrote the matrices, na? So how
No,
can we
not
tell
here
this?
for this case, no, not for here. What is the rank of matrix? I'm just asking the definition. Sorry. Okay. So I mean to say, what is the rank of a matrix?
Uh, the number of pivots.
The number of pivots.
In Yes,
Uh-huh.
sir, independent
Independent?
Vectors or independent rows.
columns.
Independent columns. Yes. So rank is, you can say if you have a 5 cross 5 matrix, then that means it have 5 rows. and independent rows mean to say how we'll get that independent row, the or how we can the number of pivot is also in different way, you can say, because number are independent row you will get by this getting the pivots. So the way it is, you will follow
Elimination, sir.
sorry, elimination method, right?
Yes, sir. Elimination.
We can follow the elimination and we'll try to find or try to convert this matrix in some kind of upper triangular, okay, where we will make it try to zero with the row operations. The row operation will try to make it zero, sorry, the below is as zero, and above is I, we even not caring whatever the number is coming, don't care, okay. But the case is that we'll try to make a upper triangular form. So either it is not becoming, even sometime could be of this one, even till here it is non-zero and these all are actually zero. So this could be a form. So means this can be, there is a possibility that this could be of this form. So number of here is how many like entries are where it's coming, the pivots. The pivots are one, you can say the pivots is coming while doing this operation. You can, let's say I have this matrix 1 1 1 0, or even let's say minus 1 0 1 and 1 0 minus 1, even minus 1 and 1. Suppose this matrix we have, we will follow the row operation. So this is 1 1 1 and we'll try, here is how we can make it 0 here. So you can add one row 2, in row 2 you can add row 1, so it will be 0 now. This is 1 and this is 2 and this is 1 1 minus 1 0. So this is how we'll try to make it with the operations, okay. So let me do it quickly. So here this is going to be 1 1 1 and this is 0 1 2. You add this, subtract, so in the next operation you can do r3 minus r1. So here is going to be 0, here is going to be minus 2, and here it is going to be 2. So see, now here is this one is your pivot element. Now you can this is not, here is, this is the, here is the pivot element and here is the pivot element, and below of it, like here is below of it 0. Also now here is, we have to make it below of it 0, so we try to make it 0 here. So we can easily do the next operation and we can easily make it 0. So this is called a pivot. So here is, we have 3 pivots, here is also going to be, and if you perform the next operation here it will be 0, and here you'll get a non-zero number which you can convert in the one, okay, and that is also a pivot. So here is 3 pivots you are getting, means all columns are independent. So by this way, how many pivots we have? 3 pivots or 3 independent columns. So rank is 3 because 3 pivots we are getting. So this is the way to get the rank. So suppose the case is, if the rank is not, you are getting, suppose here is all 0. So here you are getting 2 pivots. So rank is 2 now. So rank is 2. So in this case, there is a relation with the eigenvalues and rank. If the rank is less than, if the rank is less than this order, if it is 3 cross 3, so 3, if the rank is less than the order of the matrix, so in this case eigenvalues, you will get a fixed eigenvalue, at least one you will surely get it, which is 0. So one eigenvalue is surely is, this one is fixing that, yes, at least one, so at least one of the eigenvalue is 0. So here you will get a one eigenvalue which is 0. If you have a, this is a full rank, as here the case, this is a full rank. So in this case, this is a, this matrix don't have any 0 eigen value, okay. So this is one thing, before to start some bigger matrix thing, we can easily do something, can we think something, or it's guessable that the rank is lesser than the order of the matrix, so you can quickly decide that the matrix have at least one 0 eigenvalue. So this is one kind of trick, you can use it. And what is going to be in that case, the geometric multiplicity. What is going to be in that case? Geometric multiplicity for that, for the zero eigenvalue. So
It is
what is going to be that?
sir n minus rank of A.
N minus rank of A. Why this? What? Why this is going to be?
It is in the null space because the null space basis it contains in the null space.
So you are getting this by of particular theorem. What is that theorem I want to listen? There is by this, why, what is going to be nullity here? This is one theorem is there. What is this theorem called? Anyone?
Rank nullity theorem.
Rank nullity theorem. By that way, you can easily conclude. So as we do a minus lambda I, so we are getting 0, the eigenvalue, which is a minus 0 I. So which is, and we are finding the null space of this matrix. The null space of this matrix is nothing but the null space of just A, because this part becomes 0. So null space of A. Now null space of A, now what is the geometric multiplicity? Is the nullity of A. So there is a theorem, rank nullity theorem, rank of A plus nullity of A is equal to
N.
N. So here is this is the theorem, and now nullity you want to say what is going to be. So you can directly, nullity is going to be A minus, sorry, N minus rank of A. So by this simple formula, you just find the rank, and then you can easily decide that what is going to be the geometric multiplicity, just finding the nullity of A by N minus rank of A. So these tricks are important. Some question will be asked on these tricks, and this is the what is needed here. Some question definitely could be asked in the quizzes, and these are simple tricks and which you can use to follow without doing A minus lambda is the bigger case. So one another result, see what is here. There is one also we'll discuss the rank one matrix. So these are three lectures are very important. This is special cases and this eigenvalues and column space. So see, one relation is there. So what is the relation here? Eigenvectors of non-zero eigenvalues belongs to the column space. Column space of A. What is here happening? So the statement is every eigenvector, okay? Every eigenvector of non-zero eigenvalue, okay? Non-zero it's needed because non-zero, if it is a zero, then what is going to be? It is not
In the
inverting.
null space.
Yeah, that is, then it is going to be of null space, correct? So every of non-zero eigenvector of non-zero eigenvalue belongs to the column space of it. So how it's happening? So the case is simple. Here is, we know, right? If V is eigenvector, so AV is equal to lambda V. Correct? AV is equal to lambda V. So we can write here this as, V is equal to 1 by lambda. If lambda is non-zero, then AV. It is going to be AV. So here is this V is how we are getting this V. This V is you are getting by What is this? This a this side is nothing but your column space, right? This is just you are this is you are finding the image of this V, and whatever you are doing, this is nothing but your column space. This belongs to your column space. This belongs to your column space of A. So in the you are it's look like you the both side you have V, right? It's look like both side you have a V, but this is your one element of the column space, and which is nothing but just scaled up. This 1 by lambda is just scaling of the one of the column element, sorry, element of the column space. So that is the beauty of eigenvector. Why we are very specifically we are using eigenvectors are belongs to the column space, belongs to the null space. If you have zero eigenvalue is zero, then eigenvector belong to the null space. If non-zero eigenvector, non-zero, we are getting the eigenvector of non-zero eigenvalue, then it belongs to the column space. Okay, so this is the beauty thing, and why it is. Some question would you ask also, like, okay, let's say the question is of option wise, eigenvector belongs to the null space, row space, column space. How it is? You can check the either could we ask of eigenvector of zero eigenvalue is belongs to null space, row space, column. You can easily choose the options. If you know, then it is. So these are good tricks. Question would be asked on based on it. Now there is another important matrix which is rank 1 matrix, and it have very important property related to the eigenvalues and eigenvector. What is a rank 1 matrix? Anyone can tell?
Where only one independent row is there.
Only one independent row. Yes. Or in different way, a matrices which have rank 1, we can call it as a rank 1 matrix. Yeah.
Yes.
So rank 1 is actually a very special case, and it is actually generated by this. You have a two vector, let's say u and v. So you can say that u v transpose. Let's say I have this vector, let's say 1 2 3, okay, and another vector v is, let's say, 1 0 1. Okay, let's say u is this one and v is this one. So you can find u v transpose, which is 1 2 3, and the transpose one is going to be here 1 0 1. And if you multiply, you will get the matrix here, the 3 cross 3 matrix, and you can easily multiply. This one is multiplied with this one, 1 0 1, and see 2 is 2 0 2, 3 is 3 0 3. See how this is how the multiplication you can get, which is a 3 cross 3. And see the what is happening here. This is the main vector, and others are just the these rows are twicely of the this first vector, thrice of the first vector. So if you do the row operation and convert in the upper triangle, you will get only of this one, right? So by this way you can say only one pivot is there, so this is rank 1 matrix. It have, so sometimes I'm doing like this, so it's visible, okay, we are doing and this is what it's happening. Sometimes directly a matrix should be given and you don't know what is there. You will see only the entries, and okay, what's happening here, maybe here is more visible entries, so that's why it's okay, you are able to see. But maybe some strange numbers are given and very hidden, you don't know that. You can follow the procedure a minus lambda I, but suppose the time constraint is given and say that very quick time within the small time, it's in the exam itself, you want to reduce your work time, so you can easily use the trick. So once you guess that okay, this is rank 1 matrix, so easily you can say okay, 0 is going to be eigenvalue, how many times the eigenvector is going to be, or geometric multiplicity, algebraic multiplicity. You can easily guess that with the after knowing this is a rank 1. Like here is 0 is going to be eigenvalue, geometric multiplicity is going to be n minus 1. Because the nullity is going to be rank is 1, so nullity is going to be here is rank is 1, so nullity is going to be n minus 1. and this is going to be the nullity of or null space of dimension of the null space. So geometric multiplicity is going to be for the zero eigenvalue is n minus 1. So these are tricks. So here it is beyond these lectures contains the trick which help you in place of finding the whole bigger thing. You can easily find with the tricks. Okay. So this is the rank 1 matrix and the eigenvalues, eigenvector. Eigenvalue is going to be 0. Eigenvector is going to be eigenvector. Sorry, geometric multiplicity is going to be uh, here is not only this one. One another thing is that eigenvalue 0 is one eigenvalue and non-zero eigenvalue is going to be what? V transpose U. So 0 is one eigenvalue as the rank is n minus 1. Sorry, yeah, rank is 1. Sorry, rank is 1. Rank is 1. So 0 is eigenvalue which is lesser than. Okay, so 0 is one eigenvalue. Another eigenvalue is what is going to be? Another eigenvalue is just do the V transpose U. Here is previously to matrix is if you are this is U transpose V, but here is V transpose U is going to be one eigenvalue of the matrix, because as here if you take V transpose U, which is a scalar, you will get. So V transpose, if you do this is 101, and the U is your this one 1 2 3, and if you multiply do the dot product, you will get a single scalar. No? This is 1 time 1 plus 0 time 2 plus 1 time 3. Okay? And this is going to be 4. So 4 is going to be the eigenvalue of this matrix. And geometric multiplicity and algebraic multiplicity for this matrix is going to be same. See, geometric multiplicity and algebraic same means both are equal, and which both are equal. Geometric multiplicity and algebraic multiplicity is 1. Eigenvalue have geometric multiplicity and algebraic multiplicity both are n minus 1. So rank 1 matrices, so here is we can conclude that if you have a rank 1 matrix, then it have two eigenvalue only, which is one is 0 and the second one is V transpose U. Here as we multiplied. Okay, two eigenvalues 0 and this one. This have algebraic multiplicity n minus 1 and geometric multiplicity is also n minus 1. Here is algebraic multiplicity is 1 and geometric multiplicity is 1. Okay, this is the way you can follow to find it. Yeah, so you know if you have rank 1 matrix, it quickly guesses that if you have bigger n cross n, 5 cross 5, 6 cross 6, or maybe of very big matrix. So based on if you just quickly guess that okay this matrix is rank 1 matrix, then no need to do that a minus lambda a minus lambda a and whole procedure and find all others. No need of. Just quickly, okay, the eigenvalue is this one, eigenvector is possibly this one. Just find one of the row. The particular row you will find that, then you transpose V something you can do. You can quickly find the okay, this is going to be eigenvalue and this is going to be eigenvector. Anyone wants to ask any doubt?
Sir, please give some examples.
Example is rank 1. Okay, let me. Okay, let's say. Suppose you have this matrix. So what is going to be here eigenvalue? So this is going to be similar. Like what is going to be this case? So are all of you able to see it very quickly? Is this a rank 1 matrix? No? What is the
Yes,
rank
sir.
here?
It is a rank 1 matrix.
What about the case here?
Yes.
Let's say I'm making it. What is this? Is this rank 1 matrix or rank 2 matrix?
It is rank 2 matrix, sir.
Yes.
Okay. So this is going to be here is rank 1 matrix. If here is 0, this is rank 1 matrix. You can easily check that. Okay, this is just multiple of 3. You have the first row. This is just multiplication of the first row, no? 3 times this, 4 times this, 7 times this. This is the main row is there. And what about the, okay, so you have this row is, you have this one, 1, 2, minus 1, 0. So what is going to be non-zero eigenvalue? Can you quickly consider what is going to be non-zero eigenvalue here? Anyone?
One,
Why it is 1?
because we multiply a minus lambda I is equals to 0, right?
A minus lambda I
Is equals to
is equal to 0.
huh.
So you proceed with the all and you exactly got the non-zero eigenvalues 1.
Sir,
Yes.
3.
Why it is 3?
V transpose U, sir.
What is V and what is U here?
V is 1347.
1347. And U is, that is what here? You can quickly guess that what is going to be your V here, what is going to be your U here by looking this one. See, here it's, I made this one, so you are able to say, okay, this is my V. But here is the pattern you can follow this. This is going to be your no V and this is going to be your U, you can say. Here is also the same way. This is the, you can say this is row is, that's why I collected here. This is your V and this, let's say U is going to be, not let's say, this is going to be your U. Or you can easily quickly, if you're not able to, you can, what is happening here? 3 times this. So what is happening 3 times this? That then here is your V. This is, let's say this is V. So now what is going to be U? The second row is 3 times this vector. So the U is here the one time this one, 3 times this one, 4 times one. This is how it's multiplied. Then this matrix is built it. So this U is your this one and V is this one. So that's why here is V transpose, you are getting this bigger matrix. And by this way, you no need to now do A minus lambda I. The eigenvalues is going to be V transpose here U. So here is V is actually I wrote in the, here is in horizontal, it should be in vertically actually. So here is 1, 2. So this is your V and this is your U. And V transpose U will do, he will get here 1, 2, minus 1, 0. And it is here already V is 1, 3, 4, 7. You multiply. What is happening here? What is the scalar you are getting here? 3. 1 time 1 plus 2 time 3,
6 plus 1, 7. It should be.
7.
Yes, it's the total should be 7.
Okay. So 4 time, okay, 4 time minus 1. Yeah, this is what it is. And 0 times 7 is going to be 0. So 1 plus 6 minus 4.
Sir, it is minus 1 into 0, right?
Minus 1 into 0. Why? Minus, this is 4, no? This is 4.
Oh, sir, I thought it is 0.
No, here is 4, no? So here is 4. So. I'm not building from, I'm not putting the entries from my side. This is according to this one. This is your U and this is your V.
Yes, sir. So we'll get 3.
So by this way you are getting 3. So non-zero eigenvalue is 3. So this is a good thing, that sometime, no need to do a minus lambda I for big one. If you once quickly guessing that, okay. So whenever you have, no, this is a request again. Whenever you have a bigger matrix, just don't blindly follow this a minus lambda I. The bigger matrix purposely given to use your tricks. You cannot do by hand a minus lambda I for the 5 cross 5 or 6 cross 6 easily. It will take time. But if whenever a time taking question is given, that means surely some trick is there. Surely some hidden something information which is not provided us, but we have to check which trick I should to use. Is this zero matrix, rank one matrix, or lesser than rank one matrix? Which trick I should to use so that we can infer some information from there by just looking the matrix and reduce our work by calculating a minus lambda I or the bigger the whole procedure. Okay. Can we move to next?
Yes, sir.
Okay. So in this now, this is again 10-minute video. In this lecture, professor is discussing two special kind of eigenvector and their eigenvalues. Okay. So what is the special kind of matrices? No. So here is a special kind of uh, matrix is there, and eigenvalues is there and eigenvector. So what is happening here? Let's say you have a matrix, okay, and the matrix is a kind of this one. The row sum, the row sum of each row, okay, each row is coming fixed number. Let's say alpha, 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 alpha. When you're summing of the first row, you're getting alpha. When you're summing the second row, you are getting alpha. When you're summing the third row, you are getting alpha. Means all row sum is going to be some fixed number always you are getting. Then in that case, your eigenvalues is going to be alpha. Okay, your eigenvalues is going to be alpha. And corresponding eigenvector is no need to also compute by a minus lambda I and solve the null, find the null space. No, do you just you can remember this is a trick, no? So because this is follow for this kind of special matrix, this is already proven. You can use it. So for this eigenvalue, the eigenvector is going to be your 1 1 1 1. Each entry is going to be 1. Okay. So if row sum is you are getting at least what is the possible thing is here is not giving any what is going to be algebraic multiplicity or geometric multiplicity, because there could be a possibility that okay, for this alpha is coming, maybe this maybe two times algebraic multiplicity for this particular eigenvalue is 2, and geometric multiplicity in that case maybe 1 or 2 also, it doesn't matter. But this is the fixed thing that one eigenvector is going to be this one. The second one is maybe differ, but one is fixed, that eigenvector is going to be 1 1 1. So here is not telling about algebraic multiplicity, geometric multiplicity. It is just saying here, if you have row sum is same for each row, then that number is going to be your eigenvalue, and the corresponding eigenvector is going to be 1 1 1. Okay. So is this special case is clear? So for example, let's say I have 1 2 3 on even, let's say 1 minus 1 0. Okay, 1 1, or even not 1 1 minus 1 2. Okay, and let's say here is 2 3 minus 1 and minus 1. Let's say here is 1 1 1 0, and here is 4 7, and 3 and minus 11. See, this is the matrix we have. See, I took even very strange or very different matrix. What what is here? Anyone can tell what is the special case is happening here?
Row summation is 3, sir.
Yes.
Here is sum of each row is 3. You sum them the first row, you will get 3. Here if you sum them each row, here is 3. Here is also 3. And here is also 3. So each row sum is 3. That means you no need to now follow a minus lambda I, the bigger one. You can from here, once you are getting, quickly deduce that, okay, one eigenvalue is now fixed, which is 3. You are getting 3 as the eigenvalue. And the corresponding eigenvector is going to be 1, 1, 1, 1. This is the sure thing. And now you can use to find the other eigenvalues. Now once you know, if you blindly do a minus lambda I, okay, you will end up with the characteristic polynomial which is equal to 0, and you start finding the roots. This is a difficult thing, but once you know that, okay, 3 is one eigenvalue of it, you can start making a factor. Okay, let's break in the form of a minus, sorry, lambda minus 3, because you know 3 is eigenvalue. So lambda minus 3, and rest all you can convert that in the order of, this is going to be a power 4 polynomial, degree 4 polynomial. So you, now the rest all going to be degree 3 polynomial. Maybe in that also uh, you are coming out as a lambda, then it is going to be degree 2 polynomial. In that case you can easily, you know, uh, do the root square method and find the other roots. But the thing is that if you blindly do, if you don't know this, then you will end up with the characteristic and you can not able to proceed, because how I now factorize, how I'll get the roots, because degree 4 polynomial is not easy to solve. This is a tough thing now. But once we get this, okay, this is going to be the eigenvalue is 3, and your work is reduced a bit, and the other eigenvalues is you can easily get. Or maybe the question would be asked, find at least one eigenvalue and eigenvector. So don't do the blindly a minus lambda and follow the procedure. Check that, is this a very specific thing or a special case of matrix? Special matrix is there in this case. Okay, this is happening, then no need to do. You can argue that, okay, the row sum of each row is same, so eigenvalue is that particular number and eigenvector is going to be this one. Okay.
So, if we are getting some thing same, so it will always be only one, like all the vector one, 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 one.
Yeah, it is always going to be 1 1 1 1.
Okay, sir.
Suppose the case is it have algebraic multiplicity is 2, or maybe let's say geometric multiplicity is, in that case, is also 2. Let's say there is a possibility, we don't know, maybe here is going to be lambda 3 square while doing the factorization. Maybe you will get algebraic multiplicity is uh, 2, and geometric multiplicity is 2 also. In that case, one is the fixed thing, this is going to be one eigenvector, the second one is maybe differ. That is also not going to be 1 1. How it could be 1 1? We want two independent, that is going to be two independent eigenvector. So maybe the second one is different, but one is the sure that, okay, one is 1 1 1 is going to be one eigenvector. Okay, is this clear?
Yes, sir.
Okay, so now let's see the another case, is that if you have a matrix, okay, if you have a matrix, the special case is that the entries are filled here But let's say I have this one is one entry, right? This is here is two entry, and here is three entry, and here is four entry. Okay, this is one, this is two entry, this is three entry, and this is four entry. Okay, 4 plus 4. This is the matrix I have. But the special thing is here. Suppose let's take this 2 cross 2. This here is two entry, two entry here. This entry is very, so here is two entry is, let's say here alpha. Okay, here is alpha. But take this column. In this column, all entries are 0 except this alpha. All entries are 0 except this alpha. Here is also 0. Here is only the second place, two place is non-zero. And here is also 0. Here is also 0. Okay. Suppose this is the case. So in this case, one eigenvalue is fixed now. From here you can directly deduce that alpha is going to be eigenvalue, and the corresponding eigenvector is what is going to be here. Here is 0. The second place here is going to be 1, and rest all is going to be 0. This is the case. Okay. Let's say I am giving another example. Let's say I have this matrix which is 5 cross 5. Okay. Which is 5 cross 5. Here is going to be, let's say, entries A11. Here is A22. Here is A33. Here is A44. Here is your A55. Okay. But for the time being, here is your any, I don't know what about these all. Even I don't know what is here. This all. This is, don't think this is 0. Okay. This is any non-zero number. Okay. This all I don't know. Don't care. This all entries I don't care. But at the here, some non-zero here is, okay. Some non-zero number is there at fourth place here. Let's say here is 3. Okay. And above all are 0. Okay, and below is also 0. Here is whatever, I don't know, I don't care, any very strange number is there, I don't know what is there. Here is also maybe non-zero, 0, I don't care. But at the fourth cross 4, this column, this particular column, at the fourth cross 4, at the fourth place, 4 4, here is you are getting non-zero, and rest all are 0. So in this case, again, the eigenvalues is going to be 3. And the corresponding eigenvector, now tell what is going to be?
1 1 1.
Sorry, what is going to be?
All 1.
No.
Uh, Starting would be 0, and at that point it would be 3.
No, at that point, not 3. 1 is going to be. At that point is going to be. At that point, which, at where? The fourth place here.
Yes, sir.
Means here the fourth coordinate of this vector. 0, 0, 0. The fourth coordinate is 1. And the rest now 0.
Oh, okay, sir.
As this case is. As the at the second place it is non-zero, that number is going to eigenvalue, and the second coordinate of the vector is going to be 1, and rest all 0. And here is the same also, like here if the fourth place is non-zero, okay, here is, then eigenvalue is going to be that one, and the eigenvector is going to be, the fourth coordinate is 1, and rest all 0 in the eigenvector. This is the theorem. This all theorem is mentioned in, this is the result. Here see the thing, here is 1 and here is 1. The row sum is going to be what in that case? This is what the professor is saying. Okay. So for example, I'm making even, let's say I have this matrix. Let's say I have this matrix. Okay. And the question is asked, find the one eigenvalue, find at least
Is 5.
one eigenvalue and one eigenvector. So here, no need to proceed with the, uh, you don't need to proceed with the a minus lambda I and do all. Here you just see this column. This column is that at the diagonal entry, which is 333, sorry 33. Here is 5, and the all our entry is 0. So here quickly you can deduce that this matrix have 5 as eigenvalue, and eigenvector is going to be what?
0 0 1 0.
0 0 1 0. And anyone can tell, anyone is know that the if you have a matrix A, then matrix A have rank, sorry, matrix A have lambda eigenvalue. What is going to be the eigenvalue of A transpose? Every thought? If you have matrix A with the lambda eigenvalues, what is going to be the eigenvalues of A transpose?
We never thought, but it should be lambda.
It should be lambda. Why?
Mm, sir, row space and column space are sir same.
Hmm.
So rank would be same also.
No, rows space columns. So the rows eigenvalues are eigenvectors are going to be differ, but eigenvalues are going to be same. Can you prove it? Very simple method. Small argument can you give? You can give. Okay, so no issues. You know, right? Or it's even proved already. I think it's done. Determinant of matrix is the multiplication of eigenvalues. Is it?
So can you repeat it?
Determinant of the matrix is nothing but the multiplication of eigenvalues, correct?
Yes, sir.
And is this argument is true in the matrix A, and the determinant of matrix A and the determinant of A transpose are same, correct?
Yes, sir.
Yes, sir.
Determinant of A is equal to determinant of A transpose, okay? And the determinant of A is nothing but the multiplication of the eigenvalues, correct?
Yes, sir.
By that way, can we conclude, okay, the eigenvalues are going to be for the transpose is also going to be same? Not conclude here. Actually, we can, by this is not proof, but this is one institution, institution that intuition that these eigenvalues are going to be the same for A transpose also. This is not proof. Okay, by this way we cannot say both left side are same, so eigenvalues are going to be by this way. But this is one intuition that okay, by this way also we can say okay, eigenvalues for A transpose is going to be same. So can we deduce something from this matrix? Can you tell me another eigenvalue of this matrix using this something?
Uh,
What?
the and multiplication of lambda values would be same.
No, I want one another eigenvalue different from 5. Can you tell me? except 5, what is going to be the eigenvalue of this one? Oh, another eigenvalue.
Yes, sir, we can calculate.
What is that? No need to calculate with this, whatever just now we have seen by this method only. We just now seen this method, particular place. By that way, can we conclude something another?
I think we can only say that
Yes, sir,
the
we can conclude. One, sir, one will be another eigenvalue.
One is going to be another. Why? Why? Why it is going to be one? You said no. Manisankar?
sir, if we do the A transpose,
Hmm.
so this this is last row will
Hmm.
become the column, and then we can say that one would be one lambda.
Yes, if you let's do the transpose here. This is 5250 and 00001. Now see, this is a beauty, no? One beautiful thing we got here. This place is the fifth place is non-zero, and rest all zero. This is your A transpose. So we can talk about the eigenvalue of this one, right? We can also talk about the eigenvalue of this one. Eigenvalue of this one is going to be 1, right? We can hear from here, this one.
Yes, sir.
And eigenvalues is going to be 1 here. I said no, the eigenvalues of A and A transpose have the same. So from here we can also deduce, okay, one eigenvalue is, this eigenvalues are same. So for this one is 1. So this is also going to be one of the eigenvalue, sorry, one another eigenvalue is going to be 1. Eigenvalues are going to be same.
Sir, one doubt. Sir,
Yeah.
we said that the multiple of them would be same. We didn't say that eigenvalues would be same, because multiplication could be different by multiplying different numbers
No, so
also.
eigenvalues are actually of A and N transpose are same. We are going to see ahead. So eigenvalues for the A and A transpose have the same eigenvalues have. Okay, this is the true statement.
Okay, sir.
So from here we cannot say about the eigenvector of 1. Okay, of A we cannot say, but one result we can use from just now, that at least we sure one another eigenvalue is going to be 1. Okay, because here the eigenvector you will get for A transpose is going to be 00001, but this eigenvector may not be true for this, is also the eigenvector of this one. Okay, but yeah, eigenvalues are going to be same. Okay, so if you have a same if you have a matrix A, then eigenvalues of A and transpose is same. Use these two properties to conclude, to give at least two eigenvalues. So no need to proceed a very big thing. You can use to don't do A minus lambda I. Without doing that, we can at least conclude two eigenvalues.
Uh, and sir, how do we conclude the other values without solving whole thing?
So other is now is going to be tough now. Now you got to, now you, what you can do, you can do A minus lambda I and try to you find the characteristic polynomial of it, and you are you are very sure that 5 and 1 is going to be eigenvalue. So you can do the factorization by A minus 5 and lambda minus, sorry, lambda minus 5 lambda minus 1, and now you will get a hands on. Here is a quadratic, because this is 4 plus 4. You can easily do this factorization, is you can do, right? You can easily do, because
Yes, sir.
once you got these two, so you'll get a quadratic. And now do the square method or whatever method to follow, you can find the other roots. Okay,
Okay.
good. Okay, in the next, let's quickly eigenvalues is in the next step is the complex eigenvalues and eigenvector. So there is a possibility we have seen in already 2 cross 2 the complex eigenvalues and eigenvector. So it's repetitive actually. But yeah, there is a possibility that you have entries are real, okay, but eigenvalues may be complex. This is one thing you may not see. But the thing is that maybe the eigen, so here is the entries are maybe one. So here maybe the case is where the entries are going to be real, but eigenvalues may be complex. Okay, there is a possibility. So that is the here in the professor is in the next ahead in this session, in this lecture professor is telling the cases. So not only the complex entries are there, not surely, but complex entries are there, then there would be eigenvalues of complex number, but entries may be real also have the complex eigenvalues, like this one. This have the eigenvalues 1 minus I 1 plus I. Okay, maybe here is see the complex number are there, eigenvalues are complex. Okay, no, here is see the entries are complex but eigenvalues are real. So there is a possibility that entries may be complex, the eigenvalues may be real. As you have a Hermitian matrix, I hope you have seen. But there is a possibility also, maybe eigen entries are real but eigenvalues may be complex. So this is not so important, but this is I'm saying this could be possible thing. This is some results is some examples are there. You can take this one. These all entries are real, but eigenvalues are complex. And there is one also that eigenvalues are complex. Sorry, eigen entries are complex, but eigenvalues are real. Okay. Let's move ahead to the next. These two property, except these two, there is one another property. Important properties these have. In this lecture, now we are going to see the eigenvalues of A and A transpose have the same. See, now here is written there the eigenvalues of A and eigenvalues of and their algebraic multiplicity. See, now not only I am saying, even I was knowing to be the eigenvalues are same. Not only the eigenvalues, their algebraic multiplicity is also going to be same. This is also true. Now see, not only the eigenvalues, their algebraic multiplicities are same for the A and A transpose. Okay, and we just now solve one problem related to this. Okay, you can use it. Now next is, so one thing is there before to, what can you say about if you have matrix A, okay, and this matrix is invertible, inverse is there. If this have eigenvalues lambda, what is going to be eigenvalues for A inverse?
Will it be same?
No. Anyone else? Manishankar? Manishankar is very silent. I don't know he's there. Do you have any idea?
So he might not be here. He went somewhere.
Okay, so the inverse, the eigenvalues for the inverse is going to be 1 by lambda. Okay?
Oh, yes, sir.
Let's say you have 1, 2, 3 eigenvalues. So A inverse have 1, 1 by 2, and 1 by 3 eigenvalues. Okay. But okay, one thing is there. What about the eigenvectors?
They'll be same.
Eigenvectors are going to be same. Whatever the eigenvector for this one, this eigenvector is going to be same for this one. Whatever the eigenvector for this one, this eigenvector is going to be for this one the same. Okay. So eigenvectors are going to be same there, but eigenvalues are slightly different. Okay, this is the beauty of A and A inverse matrices. Okay, you can see the result here. Eigenvectors are identical for A and A inverse. Identical means they are same, but eigenvalues now going to be 1 upon, okay, 1 upon lambda with algebraic multiplicity k. Okay, algebraic multiplicity also may be, let's say here is 2 2. So here is 1 by 2 and 1 by 2. Yeah, it's already, because you can easily say that this is 1 by 2, this is 1. So algebraic multiplicity also same. Only the numbers are going to be in opposite of it. Okay, 1 by of. Eigenvectors are going to be same. Okay. So AM for A, okay, algebraic multiplicity and algebraic multiplicity by inverse are same. Okay, for a particular lambda. For particular lambda, eigenvectors are going to be same. Okay, for A and A inverse. For particular lambda. Okay. Okay, this here is lambda. Okay, this two are thing. This thing. Eigenvalues are going to be 1 upon of. Okay. Is this clear, Ananya?
Yes, sir.
Okay. One last property, not last. These two, one is there. If you have two matrices, these two are good. Okay. So if you have matrix A and B, okay, where the eigenvalues, let's say it have eigenvalue lambda. Okay, here is eigenvalue lambda 2. Okay, you found the eigenvector which is V here. Okay, by sudden also this eigenvector for lambda is 2 also is the same, V2. Means eigenvectors are same, eigenvalues may be differ. These two matrices, let's say in 3 cross T. Okay, this could be possible. Okay, there is a possibility V is eigenvector of it. Okay, and V is also eigenvector of B. What it means that AV is equal to lambda 1 V and BV is equal to lambda 2 V. Okay, there is a possibility eigenvectors are going to be same for different matrices. Eigenvalues are different. In that case, if you adding them, you are adding them, then eigenvalues for this one is going to be lambda 1 plus lambda 2. Okay, in that case the eigenvalues are going to be just sum them, lambda 1 plus lambda 2. Okay, and the eigenvector of that one is going to be V also itself. V is eigenvector of plus V with the eigenvalue this one. So in that case also, and the corresponding eigenvector is the same V, and the corresponding vector is going to be the same V also. Are you getting, Ananya, here?
Yes, sir.
Eigenvalues are different, eigenvectors are same. Then summing the matrix and you are finding the eigenvalues of it. The eigenvalues is just sum them eigenvalues. Okay, eigenvalues of A plus B is going to be sum them, but eigenvector is going to be the same. Okay, and not only this one, the product is also having that. If you multiply AB, the eigenvalues are going to be of that one is going to be the product of eigenvalues, and the eigenvector is going to be the corresponding eigenvector is also V. Okay, corresponding eigenvector is also going to be P. Okay, so this is a beauty thing with the two different. It is not always possible. Okay, if suppose you have a two matrices where the eigenvalues are lambda 1 and eigenvector is V1 here. You have a matrix V which lambda value is eigenvalue is lambda 2, and here is eigenvector is V2, Both are different, not same. In that case, this is not true. Okay, this is not true. Then this is not going to be eigenvalues are lambda 1 plus lambda 2. This is the case for when these two are same. Okay, this is not general case. Here is not any general. If you summing them, eigenvalues are just sum them. No, this is not true. This is the case condition you can pose it here is both should be same. Then it is a possible. Okay. Then the product and multiplication. Sorry, product and addition is the just summing them eigenvalues, the producting them eigenvalues. Okay.
Okay, sir.
Clear? Is this clear?
Yes, sir.
Okay. The last one property, see, these all actually useful, not it's not there is one another, the a power k, the power. So here is the power is actually just extension, you can say, of this one. If you have matrix k, sorry, matrix A which have eigenvalues lambda, then eigenvalue of a power k is nothing but lambda to the power k, lambda to the power k. This is just extension of this, because you know, see, if you have matrix A which is lambda with the same A, you're multiplying, then here is lambda time, so lambda square is going. So this is just extension. So if you have matrix A with the lambda eigenvalue, so a power k have the lambda k. This is just extension of the second one. One another is, if you have matrix A, okay, if you have matrix A and you have an inversible matrix S, and if you are doing A minus S, if you have S A S inverse, in that case the eigenvalues, once you multiply it, the eigenvalues, here is eigenvalues lambda, so here is eigenvalues is going to be eigenvalue, here is going to be also lambda, here is eigenvalue also going to be lambda. It doesn't affect by S. Okay, it doesn't affected by S. Eigenvalues is same. With the algebraic multiplicity also same. AM is also same of this A and this one. Eigenvector is slightly different, which is nothing but, let's say, eigenvalues for eigenvector is for this one is V. So here is nothing but, here is just S time V. The eigenvector corresponding this lambda value is going to be S time V. Okay. Here is eigenvector is going to be slightly S V. Okay. So eigenvalues are going to be same, but eigenvector is just, so eigenvector is affected, but eigenvalues is not affected. Are you getting it?
Sir, how eigenvectors would be different if eigenvalue is
No,
same?
eigenvectors are different, yes. So how it is?
Yes, sir.
So here is, see, they see how here is the proof here, Nitin. Okay, so here is, you can easily see how it is affecting. Let's say you have a no AS inverse, where the okay, you
Yeah,
have a
can you
AV
apply
is,
it on any matrices?
so here is, let's say here, see the proof how it's happening. So let's say AV is equal to lambda V, right? So you can multiply left side for this one. Yes, A. So this is going to, yes, AV is equal to, yes, lambda V, and yes, AV, and you are multiplying this side by minus inverse. So here is, yes, lambda V, yes, inverse. Okay. So here is, no. Here is, okay, no, not this one is the proper way. So here I have this one, AV is equal to lambda V. Now think about, yes, A, yes, inverse, and you're multiplying by this V. Okay, not here is, here is, what is the proof here? Simple step proof. Okay, multiply with the, okay, yes, V. So see, now suppose we have S A S inverse. Now just think about, I'm just multiplying with the vector S V. I'm just multiplying. So this is going to be, yes, A Now these two you can take in the one place. So this is going to be in yes or yes inverse yes, and this is V, and this is you can write yes A. This is going to be identity. So identity you cannot write even. This is just V. Okay, this is going to be yes V, and now this AV is your
Lambda V.
lambda V. So this means here lambda you can write, this is a scalar, so you can make it out. This is lambda SV. Now see what is happening here. This is a single vector, right? This is a vector, and this is the same vector you are getting, and this is the your matrix. Matrix and vector is going to be the lambda time the same vector. So by this way you can say SV is your eigen vector for the corresponding lambda.
So here A is matrices and S is matrix also, right?
S is another matrix, invertible matrix. Yes is
Okay.
another invertible matrix. So let's say I have this matrix A is, let's say, 1 1 2 1. Okay, let's say I have this matrix which have the lambda is eigenvalue. I have a one another matrix which is 1 1 0 1. Let's say this one. Okay, this is
Okay, sir.
invertible matrix. This is invertible matrix. Now you are multiplying S with the A and S inverse. Then eigenvalues is going to be same. It is not affected. Eigenvector is just S time. Okay, let's say eigenvector is corresponding this eigen is V. So here eigenvector is going to be SV. Okay.
Uh, so, if we go in basics, so we found the vectors like a matrix minus this lambda, whatever we will get into I is equals to 0, right?
Yeah. Yeah.
So when the eigenvalues are same and matrices is same, so how we're gonna get the different vector?
No, no. Where is the matrix is same? Where is matrix same is happening?
So that SAS inverse matrix would be same now every
No,
time.
no. Here is not, you don't compare with your diagonal. You are comparing with the diagonalizability. No, this is not your diagonalizability. Here is a very different. Yes, is any invertible matrix. Any invertible matrix. This is not yes inverse is not A. Okay, this is not true. We are thinking yes inverse is equal to A. No. Okay, this is not true. This is not true.
Okay, so sir, what's the need of multiplying this S and S
No,
inverse?
this is just, this is saying that this is actually you will see use of in your electronics system course when you have some you have a, actually this is when you have a, what is that, you can say amplifier or any transmitter or whatever the transformer or anything, when you are implied some different wave with the which is invertible, you can say, then it doesn't affect or it doesn't change your wavelength or whatever the eigenvalues are representing. So actually this is related to that. This is related to that. When you are applying and reverting, it doesn't affect the wavelength. So that's why you will see use of in the electronics course. But this is one example. This is the proof of by mathematics. This is the proof by mathematics. Okay, but this is happening.
Okay.
This is a result. You will see in the any of the electronics course. I think the proper way is, let's say I have this wave which you are representing by A, and then you are affecting a transformer. Okay, yes. So it doesn't change the wavelength. Okay, what is that wavelength? It is called or something is called. You will see in the proper word in electronics. It doesn't change that. It's just maybe the wave. The wave will be scaled up and down, but it's not going to be changed the wavelength. Okay, I don't know what is the exact word, but this is how it is.
So is it amplified signal or something?
Yeah, amplified signal.
Okay, sir.
Okay, and the last lecture is this by computer, that is by Python. Sir, professor is. But this is the beautiful implication. These are the results. Sometimes the question would be asked. Okay, Sometime you can see the question would be of this case. Let's say I have a matrix A, okay, and you have a by sudden given that yes, find, and the eigenvalues is also maybe said that okay, find the eigenvalues of lambda, okay. It said the find the eigenvalues of a, followed the a minus lambda a and you find the eigenvalues. But in the next question it is asked find the eigenvectors of S inverse. So again you don't need to follow a minus this method. You can use this result directly here, okay. It will reduce your time,
Okay, sir.
okay. Okay, and that's all for today's session also, because everything is done. We have discussed. So, how was the session like? Is this understandable? Are you getting all whatever we discussed?
Yes, sir. I have to look for the lectures first.
Just see the lectures, then you can easily connect.
Yes, sir.
Okay, thanks. Any
Thank you,
doubt?
sir.
Any doubt?
No, sir. Sir, please provide the Jeep. Uh,
Yeah, you just already told, and see responses even okay. So, she will upload.
okay, sir.
Okay, thank you. Thanks for joining.
Thank you, sir.